that the last one follow with that form. So thank you.
Morning, everyone. I want to thank the session chairs for the flexibility in the schedule because I missed my schedule in the morning. And my name is Yolin. I'm currently a postdoc at MIT Laboratory of Information and Decision Systems. And the topic I'm presenting today is the cost-effective and equitable electrification of urban transportation fleets. And this is a joint work with Percy, who was an MIT graduate student, and Antonio, who was a visiting PhD student at MIT, and our supervisor is Gordon Botwood at MIT. And we're all talking about climate change, right? Climate change is a growing concern, mostly driven by the rising carbon emissions caused by human activities. But I want to talk about some straightforward numbers for the climate change. On the left, the graph shows the sharp rise of the CO2 levels from the year of 1958, and it reflects the impact of industrialization. And on the right, the global impact, the global map shows the temperature anomalies from the year of 1880 to the year of 2022, and it illustrates the how the planet warms over the time, and all the variables emphasize the urgent need for the action in decarbonization. And while transportation is a very critical part in the decarbonization challenge, and because it contributes to around 30% of the U.S. greenhouse gas emissions in the year of 2022, and the number is more than 20% of the global emission. Is the same in the year of 2022, but we can see the left figure that it keeps rising, every year, and so it's essential to shift from the fossil fuels to the clean energy in the transportation, part. And here we focus on the key direction for electrifying transportation from fossil fuels to clean energy based on the electric vehicles. And the red figure shows that there is a sharp increase for the global electric car sales from the year of 2016 to the year of 2023. And here we show different strategies for the bus fleet charging based on their complexity. The first one is depot charging. It means that the electric vehicle can only be charged in the central depot, while the second is the in-road charging. And it means that the electric bus can be charged at terminal bus or intermediate bus stop or at the central charging stations. While the last one is the in-motion charging, and where the bus can only be charged, can be charged in transit. And these are three different charging strategies for the electric buses. And our previous work focused on the first one for the depot charging because it's the most it's a simple one, and we can have a high level picture of how the electrification in transportation can impact different things. And from the previous work, we developed a optimization model for planning the infrastructures at depot and also the electric bus fleet. And while in this project, we focus further on the in-road charging and also consider the energy equity, and building on top of the depot charging, we see different opportunities. The first one is that the operating costs are much lower for the electric buses compared with the conventional buses. And the second is that we assume that we only, we only consider the fixed routes of the public transportation. And this allows us to allocate the charging infrastructures, in a targeted manner. And the third is that using the annual charging infrastructure can reduce the impact for the grid by spreading different charging, stations in a wider and geographical locations. And the last one is that we want to prioritize electrification based on, based on some different uh, manners, such as the low income populations and maybe the low emissions for the different areas. And our objective in this project is to determine the optimal location to install the chargers for the electric buses. And also we want to determine the optimal battery nominal capacities for each electric bus. And the challenge here is that because we besides the depot charging, we consider different candidate charging locations at each stop. So that means we will have more complex computation in this larger size problem. And here shows the model, which our objective is to reduce the cost in this electrification. And the cost includes the capital cost of the buses and also the installation cost and also capital cost of the chargers at each stop. And also it includes the charging cost for the batteries with the bus operation. And the constraints we consider here is that, as I said, we assume we have a fixed route for the public transportation. And also we have a fixed schedule for each bus trip. And so we need to satisfy this all kind of limitation for this bus travel. And also we need to satisfy the battery remaining constraint for each travel, and also the other limitations for the specific bus schedule. As I said, because because building on top of the depot charging, we have more candidate stops that can install chargers. And that means we will have a large, dimensionality in the candidate stops. Here I have a example for the Great Boston area for the how many, for the size of this problem. This is this here it shows one depot, which is a cabled depot in the Great Boston area. It has 19 routes and it has more than 10,000 trips. It includes around 800 bus stops. That means this is a problem, it's impossible to solve for the optimization. And the left figure here, I shows the circles here is the circles here shows the different bus stops in this bus travel, and the size of this circle are proportional to the passing frequency for the trips for this stop. The larger the circle is, that means more trips will pass this stop. So based on this, we extract the most frequent bus stops as the candidate location to install chargers. And also we keep the first and the ending stop for each trip. So finally, we kept around 72 bus stops as the candidate location to install chargers. This has been reduced, from 800 bus stops to around 80 stops. So our problem size has been reduced dramatically. And for the charging time, we care about how much time we can charge during each stop, right? For the depot charging, we can have hours charge the bus, but for indoor charging, we only have limited time. How we extract the time is that we calculate the level time between consecutive trips. That means if a bus arrives at an ending stop, and it will departure from the stop for another trip, it will have a waiting time for different consecutive trips. We extract the lower time for this, and the left figure shows um, a different. The left figure shows the layover time for a specific bus stop. Um, in the year of 2023. And we plotted the distribution in the red figure, and it can shows the mean lower time and also the minimum time and the largest time. And the mean value for the layover time, that is the waiting time for the bus in that specific stop, can be 5 minutes in this case. And we have different cases for other stops. So, but the mean value for the layover time is around 5 minutes to 10 minutes. Some of them can be as high as half an hour, but we extracted this layover time as the potential charging time for the electric bus. And here we shows the candidate battery electric vehicles with different parameters. For example, the different capacity and the range, and also different capital cost for the vehicles. And also we have different candidate chargers, which we can decide from different levels for the power rating and also the cost. And based on the candidate electric buses and also the chargers, we do the optimization based on mixed integer linear programming. And finally, we got the results for how can we allocate the chargers in different locations of the bus. And it shows that if you see the red figure, the green box represents the location that we will finally decide to install a charger. And the results shows that it will bus stops with major transit hubs and also the intersections have more opportunity to install the chargers. I can provide a example. If you are from this Great Boston area, and the Back Bay and the Boston Common are the most busy, two of the most busy locations in this area. So in this results of the optimization, these two areas have multiple chargers, and according to their frequency of the trips and also the travel schedules. And here I shows the results for how do we allocate different numbers of electric buses according to different routes in this depot. And here we have an assumption is that we only use the battery electric buses, and we use the fixed schedule for the public transportation. And finally, the number of electric buses has been distributed in each route, and according to their travel distance and according to their frequency of the trips. And in the left, we compare the cost based on different strategies. One is the depot charging, and another is with the in-road charging. Consider the charging at stops, and it shows that we have lower cost in the in-road charging if we consider different charging strategies at each stop. And so that means with the in-road charging, we can reduce the cost of electric buses by the opportunity charging. And another question we considered is that the previous question based on if we have enough money and we will electrify the whole area in the same time, how can we allocate the different buses and the chargers? Well, the second problem is that if we don't have the enough budget or the other limitations, we have to choose which route we need to electrify first. And here we consider we consider prioritizing the electrification based on the emissions and also in low income populations. The equity here means that the demographics who benefit most from the electrification should be prioritized for updates. For example, the living near high emissions and also the low income populations. And the objective for the equity part is that we want to maximize the total riders served by the electrified routes by prioritizing the low income populations and considering the specific budget, as I said, if we have a specific budget limit, and also by satisfying a minimum level of the emission reduction. And we use the for equity part, we use the data from the sensor track for extracting the emissions data. For example, the carbon emissions, and we also have the extracted the data for the ridership of the low income population, which is open source data from the website, and also our assumption for the equity part is that we have a budget for electrifying each route. If we that means we have the assumption for the total cost of each route based on their electric bus and also the chargers. And here shows that we have different riderships and also different emission levels in different routes. And lastly, we shows a results considering maximizing the benefits of low income people, considering different levels of emission reduction. From the left figure, from the left to the right, we can show if our objective is to reduce 0% to 10% all the way to 100% of emissions, which route we should electrify first. So finally, we will get a sequence to prioritize according to the reduction levels. And here I provide a summary for the project. That is, we developed a optimization tool which can decide the location of the chargers at each stop, and also we can decide the number of electric buses we require in the depot for each route. And but this work simulation is only based on one depot. So we will need to test this model based on more scenarios in more depots, and also based on more scenarios for the chargers and also different categories of electric buses. So thank you.
The question from the board. Yeah. Thank you for everything. One question compared to if you set fast charging stations along the roads, there will be some places. I mean, the distribution system cannot provide that service. So if you include that cost in your modeling.
Oh, we didn't include the extra infrastructure in the charging. I mean, from the distribution system, but we do consider the distribution capacity limits in that location. That is, there will be a capacity in the distribution system which it can only install specific loads, and well within that.
Yes, and if again the set point in the charges. I think the distribution system, I mean, very far away from their point, so there will be a very long cable.
Oh yeah. We haven't considered that problem yet. I mean that part, but we will consider in the future. Thank you.
Okay, any other question? No, so let's move on. Thank our speaker. Let's move on to